啊，可能会。对，上个班我没有来，这个星期我没有来，不舒服。啊，他没有讲你可能失眠。不管有，我介绍吧，听说你们一起的，一定会有关系。我喜欢来一个身体，我去骑哈喽，去
已解锁，请取出话筒。
Okay. Good morning to everyone. So the replacement class schedule is out. I already put on the Moodle. Have you check it? Yeah, I think it's on week. Injay, do you know which week? Yeah, Monday 10 to 12. On which week again? I think it's week 5, week 8, week 10. Okay. Week 5 is tutorial, so you come for 1 hour. So it's next week, basically, next Monday. And then week 8 and week 10. I think around week 8 we will do one midterm. I'll let you know the scope again. See where's our pace, lecture pace. And I return you your assignment, right? So we will discuss it tomorrow. Okay, so I'll leave all your questions until tomorrow. You can discuss the mark with me tomorrow. Okay, after we discuss in class. Quiz, we will do it tomorrow as well. Okay, so we do quiz and assignment uh, discussion tomorrow. And for quiz one, right, you can check it here. Advise you better check it because so that you know how I grade your stuff and then you know what's your mistake. Or you can argue with me like if there's marks that I didn't give you properly. And I upload the quiz solution on Moodle as well. So I decided the second question to be false because I lost information last time. Basically, you have a chance to pay after the semester start. Okay, so this is the reason. But for paying part, right, I just regard any form of payment as your responsibility to pay. Okay, so you have to take care of your payment. Yes, yes. 诶，可是那时候不是讲3点前没有课吗？对对，10点到12点。你是说就一些人上来的？哦，是有几个人？3个，3个啊，3个啊不止。OK，你有没有可能问一下那个 MPU 老师，1个小时这边1个小时那边，可以问一下吗？因为 replacement 啊啊，没有，他不用改，就是让你们出来1个小时还是这样，如果能的话。你们几个人到底？4个罢了啊。OK，如果真的不能来的话就不能来。如果能的话，你跟他讲一下，看你们1小时这边1个小时那边，对，OK 吗？OK，yeah, right. So, um, maybe the payment here is not like you have to pay by yourself. The what do you call it? The action, right? Okay, but then it's your responsibility to make sure that you pay before you come to school. Right? That's why you apply scholarship before you come to school. Right? You don't apply after you come to school. Right? Yeah. Huh? Yeah. That's right. That's right. Because the school want you to come. But if you go to the other school, then you have to apply. So, just that this school wanted you to come, so they make it very easy for the process. Okay. Yeah. Okay. So this is for the quiz. Okay. Right. Um. Yeah. Any question so far? Are you by Han? Oh yes. Okay. Finally, I saw you in week 4. Okay. 也就是刚才哦，你的 visa 刚拿到还是return？明白。其实你可以先来上课啊，也就 even though 还没有加你到 system，你可以先来审。啊，OK OK，明白。OK OK，嗯，alright. Okay, any question? Any questions so far? Question from the previous lecture. No. Okay, feel free to ask. I don't want you guys to left up so quickly. So please, if you cannot keep up, please ask questions. Okay, ask a lot of questions. Okay. If not, then we'll continue with limit law then. Okay, let's continue with limit law. How about recall the definition of convergence? So we say that a sequence an converge to L. Okay, if for every epsilon greater than 0, okay, there's this capital N maybe depend on epsilon, such that for all inter n greater than n epsilon, we will get that the absolute value of an minus L is less than epsilon. At the same time, we will denote it by, then we denote it by the familiar notation limit n to infinity of an going to equals to L, or sometimes we just write an converge to L, okay, when n goes to infinity. Okay, so far so good. Okay. Okay, so let's recall some limit law. Maybe we'll just do something that we're going to prove today. So one of the limit law that we should know is suppose an goes to converge to L, Bn converge to M, okay, as n goes to infinity. Then first of all is if you take the sum of a limit, you converge to L plus M. Okay, so how do you read this convergence here actually? Okay, so well, on the right hand side here, this is just the limit of the sum of sequence here. Okay, but then what is L plus M here? So L, actually we can write it as limit of an, and then M is just limit of M. Okay, so basically this is what you see in calculus 1. Okay. And at the same time, I think like what Tian commented last time, right? So you can see that this is a linear operator, right? Or this is a linear line. Well, what's the vector space between this linear map? Do you know? Linear map, you need to talk about two vector spaces, right? So what are the two vector spaces here? What's the input? What's the output? What's the input of a limit? Sequence. Not just sequence, this is a convergent sequence. If it's divergent, then we don't really have limit law. Okay, so it's important here that here we have a convergent sequence. Okay, so the input here actually is a we call it, sometimes we call it space, actually space of, or just set of convergent sequences. And then what's the output? What's the output here? What's this limit number you can take? Real number, very good. Okay, so in linear algebra, you know that real number is a vector space. Have you shown this as a vector space before? You can take addition of sequence, right? You just add term by term, and then you can take scalar multiple of sequence, also scale by term by scale. And so it's a vector space. Okay, very good. And then next one I want to do today is products. Okay, so if you have two convergence sequence, you take the product, then the limit is also going to converge to the product of the limit. Okay, Sm go to infinity. Right. Okay, so let's show this too. For the quotient and the scalar multiple, I will leave it for exercise. I will put as my note. So let's do this too. Okay, so first one, what do you want to show? In the epsilon n terms, for every epsilon greater than 0, there exists an n such that for small n greater than n epsilon, for all small n greater than n epsilon, so if you like, there's a for all here, implies that the sum of an bn minus l plus m is less than epsilon. Okay, does it make sense? Okay, so in this class, whenever you see limit, I want you to translate into the definition of epsilon. Okay. So in this case here, what's your goal? The goal is this last part here. Okay, this last part here is your goal. Okay, you need to make sure this whole. Okay. So, like what Dulik teach you, right? So you play around with your goal first. Okay. How to play around with this goal? Okay. So what's your assumption? Do you still remember your assumption? You still remember your assumption? What's your assumption? What do you know about A N B N L M? Huh? What do you know about them? What's the relation between A N B N L and M? Good. And then Bn also goes to M. Okay, so meaning there's some epsilon n condition here, right? Okay. So this is your assumption. Right. So your goal is that one. Okay. So if you look at the definition of AN converges, right? So let's say I call this A epsilon such that n greater than n epsilon A AN minus epsilon here. Let's say this is B such that. Okay, so in this class, you don't know what to do. Write down as many definition as you can. Okay, then you will know how to put them together. All right. So you know an minus l is less than epsilon. You know bn minus m is less than epsilon, but you want this thing to be less than epsilon. Okay, so what's the connection thing? Okay, so this is an important part for this proof. Well, so let's do some working here before we prove. So is it possible to group an and minus l together? And bn and minus m together for this term here? Is it possible? Possible. I group an and l together. Yeah, good by associativity, by commutativity. Okay, so you can write an minus l. Actually, you need distributivity, right? Okay, minus l is minus 1. Okay, so here I get an minus l plus bn minus m. Right? But then you know that they are bounded by some number. But then now it's combined. Is there a way to split them up? What is the way? Triangle inequality. Okay, very good. Sum of a plus b is less than or equal to the sum of a plus sum of b. Okay, so you can use triangle inequality here to get this. Okay, so here is a triangle inequality. Maybe I drew a triangle here. Right. So, but then you want this whole thing to be bounded by epsilon. So meaning what? You can make them both of these add up to be less than epsilon, then you are good. Okay, so one way to do it is you can bound these terms by epsilon over 2. Okay. So somehow we want them to be bounded by epsilon over 2 equals to epsilon. Okay, so can we do that? Is it possible to do that? Can we bound this 2 term by epsilon given our assumption here? Can we pick epsilon over 2? Why? Because this epsilon here, right, is true for any real number. Okay, any real number. Okay, I don't care you call it epsilon, call it delta, call it gamma, whatever, but it's less than any real number. Okay, so epsilon over 2 should be some fixed number here. Okay, so since we need to show for all, right? Okay, so we're gonna start with any epsilon. So let's fix epsilon greater. Okay, so since an converge to L, Bn converge to L, okay, we can choose epsilon over 2 so that there exists Na epsilon over 2 and Nb epsilon over 2 in N such that for all N, greater or equals to Na epsilon over 2 and greater than Nb epsilon over 2, one of them we get An minus L less than epsilon over 2 and the other less than we get Bn minus M less than epsilon over 2 as well. Okay, but then in this case here, if you fix one epsilon, right, you need to find me an N epsilon such that this thing works. Okay, so there are two choices here, Na and Nb. Which one works? Or do you pick your N epsilon depend on this two? Okay, how to think about that? So in this calculation, right, you want both of this to be less than epsilon over 2, right? But then here, the first epsilon over 2 depend on Na. The second epsilon over 2 depend on Nb. So what was the relation between these two? Okay, so in your mind, you should really think of this Na, Nb as some like number, because it's a natural number, right? Okay, so let's say the first one is 100, and then the second one is 200. Okay, so do you want to choose 100 or 200? You just pick one, just pick one. Why? Because if n greater or equal to 200 converge, converge within 3 epsilon over 2 for Bn, then this n here definitely greater than 100. You will get this epsilon over 2 convergent for An as well. Okay. But let's say how about this one become 50, Na become 50, Nb become 25. Right? Which one you pick? Na or Nb? Na. Okay, because for all n greater than 50, definitely you have n greater or equal to 25. Okay, so meaning what? So we're gonna pick this n epsilon to be the what? Greater. Which one greater? Okay, that's the operation we call maximum. Maximum of these two numbers here. Which one is greater? Okay, does it make sense? Okay, so that if for all n greater than epsilon, then we will have this calculation. So basically is this whole calculation here. Or maybe I write here, imply the working we have. Okay, so in your assignment, this one is in your draft paper. You don't need to show me your solution. Okay, this is in your draft paper. So in your real solution, you write like this. Okay, so this is yeah. So this is a bit like what you call the you know what's a 买家秀 and 卖家秀？互弄，来解释一下，帮我解释一下，什么是买家秀、卖家秀？ Yeah. So this is your working. This is a mathematician work, but this is how mathematicians show people their work. Understand? Okay. We show something that's already fully furnished. But when you try to work things out, this is what you do. Okay. Any question? Any question for this one? Okay. So the technique here is really applying the for all condition in the convergence, and then choose the maximum of the two numbers. Okay. It's not always you need to choose maximum. You need to think about it whether you want the maximum or minimum. Okay. Next, let's do. Okay, let's do the products one. So I want to show for all epsilon greater than 0, there exists an n epsilon in n such that for all little n greater than n epsilon, we will get absolute value of a n b n minus l times m less than epsilon. Okay, we have the same assumption here. So what do you think? So assumption looks something like this. Some part of the assumption looks like this. An minus L less than epsilon. I didn't write out all the condition. What do you think? How can you combine them into An minus Bn here? Any idea? Maybe something you could try is you want to have something like An minus L, B minus L, something like that. Maybe some of one way you could try is this. But then you will get extra term here, right? Redundant term. Sorry, no wonder so weird. Okay. Yes, and yes. Okay. But then the sign is not correct, and then you have two extra thing here. Okay. So anyway, we can make it closer to what we want. Okay. So what should I do? Turn the LM into plus 2LM. Oh, okay, I get what you mean. So you mean add a LM plus a negative LM, is it? Okay, good. So, but then can you control this junk here? Is it possible to control this junk? Distribute? I get what you say. So AN, BN, so I'm gonna distribute plus L times BN, sorry, so M minus BM, right? And then plus M times L minus AN. Here is what? Here is BN. And then here is minus LM, right? Okay, good. But then the thing is, you recover the term that you don't know, that you wanted to show that is less than epsilon. And then, okay, I know that these two I can bound by epsilon. That's good. But then I still recover this thing that I don't know. So I'm trying to bound this term with something that I know. Right. So if successful, right, maybe I can just have epsilon times epsilon. Isn't it right? Okay, but then not very good. But don't give up yet. We can do something else. Okay, we don't just stop here. Okay, maybe I leave these things here first, so that you know how we fail and then how we should proceed with failure. Okay, so what else we can do here? Let's say again. L M. Oh. You mean like this? Oh, you mean like this? Okay. Yeah. So okay. So yeah. Sure. I mean, you could try, right? Okay. So you want to use like triangle inequality, you know? Okay, but then the problem here is how do you like use that assumption? Okay, you need somehow an minus L and bn minus L to come in, so that you have this epsilon thing to come in, right? But then here you separate your L and M. Okay, sure. And like you can do what Yi Hang, right? Sorry, Hang Yi, right? Hang Yi say maybe you add a okay, add a something extra, right? So for example, like like LBN maybe. So ANL maybe something like that. Right. Let's do one term first. Let's modify one term. So let me give you an idea. So maybe you get something like this. Okay. Then this term you can bound by epsilon. Okay. If you bound this term by epsilon, but this term is troublesome. Why is it troublesome? Because this term AN, you could imagine, I don't know how big it can go. You know what I say? Okay. Because if this thing is epsilon, let's say 0.001, who knows this AN is a 1 trillion? Okay, so you need to have some sort of control on AN actually. Okay, if you want to really bound it. Okay. Okay. So I think I give enough hints already. So let's do the real job here, and then I'll tell you how we can bound this AN here. Okay, so maybe we will continue. Okay, so one way to do it is I will just introduce this extra term, which is LBN. Okay, so why this LBN would help here? Because I'm going to write it as AN minus L times BN plus L times BN minus M. Okay, so that I can use triangle inequality here to get absolute value of AN minus L times absolute value of BN, and then plus absolute value of L times absolute value of BN minus M, like this. Okay. So, right. So there are two terms appear again. So you might think that, oh, I want to bound this by epsilon over 2, this one by epsilon over 2. So if I want this to be epsilon over 2, how should I bound Bn minus n? Yeah, epsilon over 2L. L is a constant, doesn't matter. But here is a problem. Can I bound by epsilon over 2Bn? Oh, very funny, eh? Epsilon over 2Bn. What does it mean? It means that for different n, you take different Bn. Okay. So the problem of taking different Bn is your capital N might not work always. Okay, so that's the problem here. But then there's something come to help. Okay, which is lemma here. So this lemma is very important. It says that any convergent sequence actually is bounded. Okay, any convergent sequence actually is bounded. Do you know what it means?
More n, can you have an upper bound and lower bound for all the n greater than distinct?
Yes. Okay. Yeah. Right. So more precisely, if Bn converges to M, then there exists a K such that the value of Bn is K for all n. Okay, so the picture that should occur to your mind is your sequence maybe going from very large place and then converge to something, then it should be bounded above and below. If you cannot bound this, then this guy should diverge already. Okay, so how to prove this? Maybe we should prove this. Okay, so do you want to prove this first, or do you want to see how this lemma get used here? Which one you want to do first? I'm not sure. Some people would say, I want to see how to use first before I want to know what is true. Or some people want to say, prove me it's true first before you use it. So what kind of person you are in this class? Huh? What kind of person you are? 拼接.
Yeah, well, I'm a bit forgotten.
Okay. Okay. Let's do the other one. Okay. So how we're gonna use lemma to this term here? To this working here. We know that Bn is conversion, converging, right? So meaning what? Meaning this term is bounded. Okay, so you can actually bound this term by some number. So I should write, what should I write? Okay, so wait, let me think a little bit. Okay, so we could write it as, so should I write equal less than equal? Okay, less than equal. Okay. So this is less than equals to the sum of an minus L times k. This k is positive or negative? Yeah, it should be positive, right, in this case here. Greater or equal to 0? Could be 0 if your Bn is constant sequence 0. Okay. Or if it's 0, then we can make it strictly greater than 0. So I can just pick the bigger thing. So make it strictly greater than 0. Then this one is a plus. Where's my plus? Okay, plus absolute value of L times absolute Bn. Okay, and then from here, we can choose like epsilon over 2k and then epsilon over 2L, right? But then is there a way to make this epsilon choice consistent? Maybe we can choose the same epsilon. So one of them we want k, one of them we can need L. So why not we just take the sum of those two, make it larger a bit. So meaning making this epsilon even smaller, okay, so that we will get epsilon over strictly less than epsilon over 2 plus epsilon over 2, which is okay. Yeah. Why? Why? It's just a preference. Yeah. K or L. Maybe this one epsilon. Epsilon. Sorry? Sorry? Say again. It's a choice. It's a choice here. It's a choice here. It's a choice here.
The K plus modulus of L is
Like
0.5.
doesn't matter.
Then
But the convergence will tell me it works.
but it's not, but it will no longer be smaller. Then we can write the smaller side. So
Oh, you mean?
I mean you cannot do by
Wait.
modulus
Wait, let me
plus
think. Okay, I think I get what you mean. So let me think. Wait, let me think. Let me think a little bit. Let me think a little bit. Let me think a little bit. So wait, let me think. So you mean that it might not be less than 1? Let me think. Is it true? Not true, eh? So let me think. Let me write what I say here. So k over k plus L, and then L over L plus k. So my claim is these two things are less than 1. Okay, so let's see what's your concern. K. Yeah.
Then we didn't write K and modulus of L at the
What do you mean numerator?
the
Oh, sorry. I think I should put put a K here and then I should put a L. Yeah. Sorry. I think I forgot to, yeah. I'm just replacing the absolute, the distance. Yeah. Okay. I think that's what I'm missing. So, okay, that's good. So I should put the K here and then I should put a, okay. So also good. Okay. I'm just like picking the absolute for these conversions. I forgot the K. Okay. Makes sense. Does it make sense? Any question? No question? Yeah. Pinje. What do you think?
I think the one works only if at least one of the key or L on zero.
Yes. We make sure they are non-zero. Oh, you mean L might be zero? Let me think. Let me think first. If L is zero, that means doesn't matter as well, right? Doesn't matter, I guess. Yeah, sure. Okay. I think the purpose we did this also because of the L being zero, so that the K can save it. So K can save it.
You must choose something that is non zero.
Yes, that's right. That's why I modified in my lemma here. It's really going zero. Because if you can bound it by zero, let's say your Bn is 0, 0, 0, 0, right? You can use zero to bound it, right? But then if you can use zero bounded, make sure you can use one to bound it. So yeah, that's the problem. I think that's another problem here. If you just consider epsilon over 2L, this L could be zero, then you divide by zero, this is not. Okay, so be careful. So in this class, you need to be careful when you're gonna divide by some constant. Make sure it is not zero. Yeah. Okay, so this technique we're gonna save your epsilon over 2L also. Okay, if the L turn out to be zero, then you are GG. Okay. Does it make sense? Okay. Okay. So should I write in full or you are happy now? Are you happy? If I write the working, can you like repeat this the whole step here, the blue part here? So you're gonna pick epsilon over 2 times K plus L. This one also pick epsilon over 2 times K plus L, and then here you also choose maximum of them, and then you will have the working part. Yes. Okay. Okay. Any questions so far? Any question? Any question? Wait, let me see. Right. So shall we prove this? Shall I prove this? This proof is very not hard. But then it's very technical. Okay, but this technique I think you should learn. Okay, you should learn this technique. Okay, you should learn this technique. So what's the idea here? So what's the idea here? Well, I mean, like, you know the convergence, right? Okay, you know your convergence here, M. Okay. So actually, you know that your terms is like squeeze maybe some epsilon. But then there's some extra terms here, right? Okay. But then did you notice that this extra term actually is finite? It cannot occur at the back. If it occurs at the back, then you don't tell me it converges. Okay, if these things happens, you don't tell me this sequence can converge. Okay, so the finitely many terms here is it's not within the string. So you can just pick the maximum one. Okay, so this is the idea. Okay, so let's write down the proof. Okay, so let's write down the proof. So, well, so what we're gonna do is we pick epsilon to be 1. Okay, so this is our epsilon. Then we have Bn minus M less than 1. Okay, so we're gonna pick epsilon less than 1. And from here, is it clear that I can write this? epsilon of absolute value of Bn is less than absolute of m plus 1. Is it easy to see this? Is it easy to see this? Huh? You don't think so, huh? You don't think so? I also don't think so. Okay, but then I suggest you to prove this lemma. I prove in class, I guess. Similar technique. But then if you don't think so, you need to prove this lemma. So this is the lemma you need here. So for every A, B in R, for all C greater than 0, if absolute value of A minus B less than C, then actually the absolute value of A less than the absolute value of B plus C. Okay, you're gonna prove this. You have to prove this. Okay, yeah, try and prove this. I think the technique used is the one that we have seen before. Okay, right. So then let's accept this first. Yes.
Yeah, this is easy.
Can be easy derived. So how?
This of A minus then for equal to of modulus of A plus modulus of B.
Yeah, sure. This one triangle
So
inequality.
technically, you receive modulus of A minus B.
But why you love?
Wait, then I cannot do anything.
Okay, you need to try again. You try again. You try again. Okay, I think it's not directly using triangle inequality, but use the method that we proved triangle inequality. Okay, so where am I talking about? Okay, if you like, maybe I can draw some intuition for you. Okay, let me draw some intuition for you for this thing. What am I aiming here? So your Bn is here, right? And then your M is within distance 1. Okay, so your M could be appearing somewhere around here and here. Less than 1. Okay, and then what is the absolute value of Bn less than M is greater than plus? Okay, okay. Let's say our zero is here. Let's say our zero is here. Okay, so if your M is occurring around here, so the absolute of Bn either is already less than M, absolute value of M, or if your M appears somewhere here, you plus a 1 will be greater than B. Does it make sense? Okay, this is the content of this. You can try and prove this. Okay. If you don't understand, just try and prove it. Okay. But then this is the picture if you regard this Bn to be positive. Okay. So if let's say we know that this is true, then what's the bound we had here? Then what's the bound we had here? Okay, so we only know that. Okay, we only know that within epsilon equals to 1, we know that all these Bn will be bounded by this term here. But how about the previous term here? Okay, so we need to choose. So therefore, for every n in n, we actually can pick our bound to be k, which is defined as the maximum of the absolute value of b1, absolute value of b2, up to absolute value of b of n1, yeah, n1, okay, minus 1. And then absolute value of m plus 1, okay? Okay, so do you know what this means here? Okay, so these are the finite things we should compare. Okay, with the absolute value of n plus. Okay. Yeah. Because you know that for Bn, n greater or equal to n1, you'll be bounded by this term, right? But then the previous one, I don't know. So I need to compare them. Okay, see which one is the larger one. So in this picture, right? So in this picture, maybe this term, okay, maybe this term here is b of n1. Okay, so you need to pick all the b of n1 minus 1, and then b of n1 minus 2, and then up to b1, you need to compare them. Which one is the largest one? So in this picture, b1 is the largest one. And then did you note that I did a trick there? I put modulus here. I put modulus. Okay, so that we consider the positive part. Yeah. Yes. Yeah. You got the proof? Very simple, very simple. Okay. Okay, wait, before that, everyone okay with this bounded proof? A question? Question? It's okay. I pick among these finite things the maximum one. Does it make sense? Why I pick until bn1 minus 1? Okay. Because for n greater than n1, I already have this bound for my thing. The previous one, you need to check. Okay. Okay. Helen, okay. Good. Okay. Like proof of lemma.
Use assume modulus of A minus B is less than C.
Assume.
And then C the particular number of
Yeah. Yeah, okay. And then
we have
assume what? Assume what? Second. Assume
everything
again, other than that, do you need to assume anything
except for the
except for the last one?
yeah, and then we have modulus of A
Mhm.
B plus A minus B
B plus A minus C. Yeah, sure, yeah.
is less than or equal to modulus of B
Mm-hmm.
plus modulus of A minus B.
Sure, good.
It's less than modulus of B plus C.
It's less than
Modulus of B plus C.
like this.
Plus C.
Plus C. Yes. Yeah.
Yeah.
Yeah. Okay, good. Yeah, that's it.
This
Yeah, that's it. Good. Yeah. That's it. Yeah. Yeah. No assume. Not. Okay. Yeah, good. Yeah. That's it. Yeah. Yeah. Any question? A question? But I mean, like in this picture, also easy to see, right? It should be true. Can see or not, Ping Jie? If cannot see, you really have to go back and drink about this. You should see from this picture. Okay. So two things I want you to do in this class. Okay. One is you need to write mathematically. Two is you need to think. Okay, these two things is very hard to achieve at once. And so you need to start with one at least. If you are very good with this, then you need to brush on this skill. If you are very good in writing this, you should imagine what you write. Understand what I'm saying? Okay, this is a very important skill. Okay, 9:50. Okay, so before we break, I think Tianle, right? Tianle give me an assignment. Tianle presentation is very interesting. I asked him to present question and give a lot of questions. He'll start by asking question. Okay, sure. Yeah. I found out that you say you want to be a teacher, is it?
no.
You should be a good teacher. You ask a lot of questions to your student. Okay. So what's your do you still remember what's your question asking? You still remember what? 对。
between n and n plus 1 or integers.
Yeah, right. That's one. Yeah, that's it. That's the one. Okay. And actually, Le Tian asked me how okay, Le, sorry, I confused. I have a friend called Le Tian. But then okay. So Tianle asked me how to do presentation. What do you think? How your presentation should be? Should you write first or you talk first or you talk first or you write? Both together. Okay, usually it's both together because this will control your talking pace. You understand what I say? Okay, so try to write while you speak. Okay, this will control your talking pace. Yeah. You won't talk too fast, you won't talk too slow. Because you need to write at the same. Okay. Well, okay, so actually I can prove for you that for all m in Z, there don't exist an n in Z such that m less than n less than n plus 1. I think in the tutorial you need 2 and 3, huh? Or 3 and 4. 2 and 3, okay. I can prove for you for all integers Z. But then I state it as a corollary, right? So that means what? Actually, I need to prove some other statement first. Okay, so I'm gonna just prove it to you that there's no integer. There's no integer. N such that n is in between 0 and 1. Okay, then from here I can deduce for all. Okay, let's prove this. Actually, not too hard. So again, let's write down what do you want to show. We're gonna write it as a set form. Okay. Why I use set? Later you'll know why. So let's define this set here. Set of integers such that 0, it is squeezed between 0 and 1, and then this thing is empty. Okay, so suppose for the set of contradiction, this is non-empty. This is a non-empty set, huh? Okay, so in this class, you need to be sensitive about non-empty set of numbers. If it is bounded above or below, what do you get? This is a very important thing. But in this case here, this is bounded below. Right? Actually, it's bounded above as well. Okay, but then it doesn't matter for our purpose. Okay, if it's bounded below, actually, I think I proved it to you last time, right? Or maybe I show it to you, or you do it in your assignment. By well-ordering principle, well-ordering principle says what? Yes, there exists a least element. Let's call it n epsilon in this case. Okay, but what did you see about this least element here? It should satisfy the set condition, right? So it should squeeze in between 0 and 1. But then order preserving property, what does it tell you? 0 is less than n naught square less than n naught, but you know that n naught is less than 1. So what did you see here? You found something smaller than n naught. Okay, so contradicting that n naught being the least element in X. Okay, this is also a proof that why numbers in between 0 and 1, after you square it, it becomes smaller. Like 0.5, you square it, becomes 0.25. Okay, so you found an even smaller thing. So that means what? There doesn't exist a integer such that n is in between 0 and 1. Okay, so done. Okay, so well-ordering principle. Okay, very important here. So how do you deduce for OM? How did you deduce for OM here? Plus integer m. Yeah, sure. Okay. So yeah. So suppose that there exists such mn in Z. Okay, then you have m less than n less than n plus 1, right? But then you obviously can take inverse of m on all of them, right? Then you get this. Okay, so what does this mean? But this has a contradiction because n minus m is still an integer. But previously I told you that there's nothing inside it. Okay, so contradicting the previous theorem. Okay, if there exists, then you will find an integer in between 0 and 1. But this is a contradiction. Okay, any question? Okay, so instead of plus m, right, I use minus m because I need to relate back to what we know. Okay, the logic is not like I cannot find this, I plus m also cannot find. The logic is I'm moving back to the previous case we know, and that place I cannot find. Then imply that if I plus m also no use. Okay, question? Any question? No question. Okay, if no question, let's take a break. The quiz is here. You can take a picture, but you cannot bring back because I need to submit later to the school. Okay, so you can take your quiz here, and then you can take a picture, take a record for your revision. And then you can try and sign in. I will open out the attendance site. Let's break until 10:57. Oh, sorry, 10:07. Okay, I already start the attendance, so you can sign in. Okay, thanks. Check it. You know here, chúng ta bị hình chữ xiên子晴，子晴，你子晴，OK。文伟，文伟 here 了，哦，要文伟，你先进群，一兴 here 新年红节上。Can we not here？没有。你该什么？好，随时。生病？怎么？干嘛生病？他是有生病，是不是？好，OK。传染。Alan 红军本书诗慧呢？诗慧是那个高高，在你旁边。OK， 好。天乐、启阳、品杰、刘长浩的李成玉 here 啊，李成玉。Hey, Chanyu, can you come here? Chanyu, can you come here? I want to talk to you about your assignment. 百涵、华月。Yeah,你发给我那个你的那个想哎嗨嗨啊哦百涵 OK 你也过来一下，我顺便跟你讲一个东西。行，你要问东西还是？OK OK 我先说 OK 好，我先说。等下我找一下你，诶，恒玉是你对不对？哦，这是我发给你的，你有看到我发给你的那个 number 吗？那个邮件，你不是发我邮件吗？你要 report，
我天可能没看。
耶，你 try 看一下。So 你好像少了很多东西，你 proof me 打出来，然后你的
看到了，昨天。
对，你的那些 definition 没有打出来，懂什么意思吗？就这些，
我知道。
知道哈。然后你的 proof 没有打，你知道什么是 proof 吗？
知道。
知道哈 ，OK。 然后你有什么东西还没做？等一下我给你看一下你的同学做的。
看到
啊，对，那个是其中一个，这个是另外一个课的，我可以给你看一下你另外一个同学的，他叫做陈宇，叫做陈
对，我看你，啊，你有什么给我？
李成宇。If you don't understand the marking, you can try and check with me. 为了等一下我看一下你同学发给我。张恒玉在 OK， 对，太多人找不到 OK， 对，如果你看一下他做的，对他，他这个 definition， 然后你看有 theorem， 有 proof，OK， 有 theorem， 有 proof，OK， 然后有一个 summary， 然后有一个题目。没有，不用抱歉，
我回去改。
好，大家再发给我。
两个事情，一个是我会子已经没参加，
什么？
会子
哦，奎西没参加。
对，
你也是没参加，对不对？对，我明白。没参加哈。我想一下怎么办。我看一下需不需要再补，如果不用补的话，我们就当做你过。因为对呀，希望就是看你之后成绩啦。如果你之后成绩不太好，就可能要补一个什么。如果 OK 的话，我们就当做你也是来啊什么的，有点麻烦。但是就是看一下怎么样啊。
还有
先暂时就是先把该做的东西做好先，如果不够好的话，可能就需要你们补一下。
明白。
你懂。But then 你们两个，因为你们两个也没有开一开始，所以我是安排你们两个打那个 lecture 1跟2材料的。对，所以差不多时间应该可以交了。
都不知道要做什么
啊，都不知道要做什么。
对，
这样我刚才 show 给你朋友看了，就是把它打出来吧。就是你看，这样子，然后你把它 lecture 1跟2，然后你就把它打出来哦。latex 哦 ，overleaf 可以 latex、text maker 什么都可以，把 latex overleaf 可以，你看它打出来，然后 definition 打出来，然后 theorem 打出来，然后它的 proof 打出来，全部打出来就可以。
这跟上课笔记的整理
没有错。exactly。
我记得上课的话也要做1和2是吧？
对，你做 lecture 1好像你们两个都是 lecture 1。
对，我们
呀，你们两个打一模一样的东西，but then 你们的 design 应该要不一样啊，你要把它变成比较有趣。然后当然你们要读完过后做你们自己的一些 summary。
我们两个做一个还是一个？
没有，分开做，自己做自己的。
自己做自己的。
所以肯定会有自己的看法或自己的想法。
一个是笔记整理，还有要加一个自己的 summary。
对，加一个 summary， 还有加一个题目。题目有3种类型啊，一种类型是true false question， 然后一种是 example。其实这个不是 example 啦，我会告诉他但是就是 example 咯。知道什么是 example？ 一个例子。班上我不是有那种例子类似有题目这样子，一个不错的题目这样子。我在班上是会有例子的嘛，I mean like 比如说，我会有来 ，OK， 给你看一下例子是怎样讲的。怎么去看啊？比如说这个例子哦，我教了 conversion 过后，可能我就说一个 conversion 的例子哦，那你可以说write down a sequence that converges and write down a sequence that doesn't converge example 啦。但是你看你的内容是什么呢？
然后最后一个
就是 proof 证明题，找一种。OK，好。
明天后午教。
能的话这个礼拜了，因为现在已经 week 几了 ，week 5了 ，so week 4，week 4，通常我们是下一个 week 交啊，但是你们还是可以改啊，这段时间内把人先交一份上来。 好，yes，没问题。你现在说的，OK，我看看
就。是说，一个这个 management 没有，
就是你看啊，我的问题是你要 define no money，but then 你 no money 还没有告诉我怎么 define，你去拿这个 no money 去 define 一个 function，有什么事呢？你都还没有决定，我还没有决定怎么知道这个 no money 啊，你就开始
但是这个 no money，我这个 no money 是说 account has no money，不是说 management has。
他的意思就是你用同一个字了。
对啊，这个字眼就
同
是
一个字眼
不知道，
这不是因为是一个部门 no money 和一个账户 no money 是两个概念。
还有
那你定义了没 ？no money in account 我不认识这个字，不认识这个，我不熟啊。
主要是 no money 是什么意思？
对啊，我要把它搬到另外一个我懂的东西上面。
不过这里讲我写不见，在做非法的东西，非法交易，
很恐怖哎、你很恐怖你。
我感觉你是故意找我分扣啊。
等一下，我解决掉一个，明白吗？明白吗？就是说你不能够用同一个字眼又放去另外一个世界里面，除非在这世界里我知道，但是在这世界里，我觉得我也不知道。你说我 account 没有 money，跟我讲 management money， 你觉得我会差很多没？差不多啊，其实差不多啊。你还是要告诉我什么是 no money，
就好像我定义 no money 是0块钱什么之类嘛，对
啊，something like that，就是一个数学，就是要把它变成一个我可以检验那种字，就是可能一个数字咯，可能你就说 account balance， 这样我就懂了。你懂吗？我觉得一个数字我可以检查。
对，我是讲
你明白吗
0 US dollars， 实际上我这个是我定义0 US dollars。
怎么我扣你很多分呢？
我不懂啊，你叫我做非法交易吗？
我扣你几分？我忘记了，我扣你几分？
那题给
谁？你还是他？哦，他的 OK， 那题是2分还是什么？2分哈，2分哈。
没有，然后问你哪里看得出有做什么非法
OK， 对 ，OK， 你 OK 吗？你明白我讲吗？你懂我讲什么先吗？你可以选择不接受，但是你知道我在讲什么。OK， 这样 OK。如果你不接受，我也没有办法。真的，我真的，因为在数学的世界里啊，你在重用同一个词啊，是很危险。啊，我们通常会把它搬去另外一个地方，可以能够检验的地方，明白吗？那哪个？
因为前一个有问题。
这个对，确实 give the fact that at least 这题是几分？3分是吗？
还是3分？你看我这拿到3分
2加3加5。
OK， 所以你觉得你这个可以拿多一点？你 argue 给我听看。
不是，
这个答案应该
你说这题还是这题？
这题
这题 OK。你这样对啊，你 argue 给我看哪里有分呢？因为可能我 miss 掉。
就我
说假设你有这个 no money 啊，give the fact that 什么意思呢 ？give the fact that there's 哦，yeah sure OK。所以说你看咯 give the fact that there are no money， 所以我要去哪里检查呢？你又不告诉我怎样检查这个 no money， 你又叫我去检查，是不是很难检查？现在你明白我讲什么吗？你明白我讲对不对？所以如果你讲no money 是 account 是 balance zero，OK， 这样我去找它 balance 是不是0？对，我只是扣你道德分。
你扣我道德分。
OK 啊，你 OK 啊 ，OK 好。对，我觉得你违反了我的那个 realistic 的那个东西，就是不 make sense， 你懂吗？他就算没有 US dollar， 他也可以很有钱啊。
它是一个 unit 嘛，currency unit 啊。
对啊，但是就是来你，然后我就说你就是来，你就是给他一个机会，给他逃脱啊。
就像比如说我有400多令吉，就相当于我大概有100美元左右啊。
那你没有讲啊？那你只是说我要找他的 US 这个 currency 的钱罢了嘛？你没有讲 equivalent， 你要讲 equivalent 啊，对吧？要讲 equivalent。
Money is a measurement whose unit can be the United States of America dollar。
对，这个 OK， 我是想你应该要说 equivalent to 0 USD 的。你如果讲0 USD， 我就讲我真的要去找他有没有这个美金多少钱的，你懂什么意思吗？
我认为每一个人都有美金啊，
没事。
我认为你也是有美金的。
就没有啦，你去check 一下，我就是没有。
有啊，我只要做拿电话，然后去设置个卡系哦，转一下。
所以我就讲你要转那个字叫做 equivalent，你要说 zero equivalent，这样我就 OK，因为你要分析嘛，我 OK 嘛。但是你要 equivalent，但是你如果只写
就一过转，因为
不可以，因为它是像你讲的，你要转钱那个转钱那个意思就是 equivalent 了啊，不然的话，因为你如果讲 USD 零的话，这样它有 RM 几百万，你讲它没有钱，这样不是很离谱？
你讲的东西，就像你跟我讲哦
，OK 吗？
零 KM 并不代表它是零米的样子
啊，还有事情，哈什么？
你讲的东西就是要跟我讲零 KM 不是零米的。
他说
你跟我讲的东西就是零 KM 不是零米的，零 CM 不是
equivalent，对，
什么东西
equivalent，
就像你讲
一个字叫
你的
啊，你就
刚刚就是用这个就可以做。
OK，说说看，做看，做看，
然后对，就指出来，
对，
这等于
喂，what do you mean？
就这个
把then我们要的是这个不是？我们要的是这个，
现在此刻的
说这个假去要，假设你懂这个
英文里面我们不用
假去要这个，
所以就是现在的。
因为这个东西包摆，这个东西包摆
我不讲
上面漆，然后包摆
什么会，我不是我讲，
也可以，
现在此刻的。就是零 KM 等于零这样子
，OK 嘛 ，happy 嘛，七样，
有一点不 happy 关于 unit 这方面，
你不 happy，但是你懂我讲什么吗？
我也听不懂，
喂，不要假装听不懂，不要假装，听得懂，不要假装，
没有，因为
你可以不接受，但是你一定要听懂先。
我不接受也听不懂，你听不懂你的逻辑在哪里？
我是跟你讲啊 ，equivalent 你要讲 equivalent， 那个字叫做 equivalent。你是不是跟我讲？你刚才是不是跟我讲要换钱？是不是要换钱？换钱这个 process 叫做 equivalent。你是不是讲换钱？
换钱其实是个文，
一定要换嘛，对不对？
不一定。
不一定，这样就错了，这样错，这样错，这样我就讲错，因为它有1000万呢，有1 trillion 呢，是不是？
这个
OK， 冷静，你冷静一点，你冷静。
0.25美元左右。你冷静。大概是0.25。
谷歌是不是要有 up and down 那个换钱？是不是？
那个没有过。没有equivalent，而且
一个人，
我讲没有equivalent，他没有过。
冷静，想好来，枪，想好来，想好来，想好来一点。
你说要换钱，
对，换钱，
你要换这个十字记，我们这个指令或者是硬币的时候，你要
冷静，枪冷静，是不是要换钱？你 agree 吗？要换钱？
我 agree。
这样就错了，你不换钱就错了，真的，你冷静一点。对，通常我们会写 equivalent， 真的，我们数学真的是会写 equivalent， 真的，因为哇，你跟我老板一样，我跟我老板讲 define 这个是什么？老板讲这个不是数学，对啊，你跟数学家讲这个不是数学，敢打，OK，it's OK， 反正就是like
这里可能有
it's OK， 我老板 OK 然后因为就是通常我们会加一个 equivalent 啊。如果你是那个意思啊，你就想把所有的东西看成它的话，我们会放 equivalent。precise 吗？你不是要跟我讲要 precise 一点啊？但是这个是数学课，所以它是数学啊。OK，sure，OK，在平时世界里面是 subjective， 然后把我放在这个课，我就是把它变成 objective。
可是我本就看它都不像这个数学题。
数学题啊 ，Why not？Why not？Why not？So make sense? Why not? Why not? 对，然后今天又不要细节了，是不是？他就是喜欢他要他的东西吧？这个人，我知道了，他的 pattern 了。然后我就跟你讲， OK，不要硬凹，讲好好来。
我这个也数学以外的东西，我学家你看不了。
我觉得可以，
我觉得可以，
我觉得可以，这是我的 philosophy。
第二个变，
你不要接受跟紧，反正就是会脱分。
你再跟我关系吧。
你觉得 aggressive 啊？
对，我觉得，
我觉得我要 inclusive 啊。
我觉得
我要 inclusive，我要 inclusive，yeah，你会觉得说，like，right，but then，我觉得这个是一个很 natural 的东西，对，比如说语言这个东西就很 natural，你可以说我不要接受语言，说你 fail 你的英文是不是？
没有那个叫什么？
啊，
那个
什么？
那个 eco 那个 economy
？economy 的那一个？
哦，就那个
哪个？
我一个没学过。
哦，
对，那个我不知道为什么你 fail 了，but then 就是语言就是这个东西，你不可以说哦，我不要接受，我不要接受你的大英系统，我不要接受，我不要你的大华系统，我不要接受。我不要接受咯，等系统制裁你哦，系统制裁你哦，你就 fail 吧。
这个是英文，
所以我就告诉你，我告诉你的，我想要教你或者告诉你的东西，就是这个是我们就是这些数学家或者这些人是怎么去想这些东西，或者怎样去看这些观点。你可以说哦，我在平常人世界，我不要这样子去看这个东西。你可以做这个选择，but then 在这个数学课里面，我们就是做另外一个选择。然后我觉得 my task is like I want to make this world a bit more organized, a bit more, maybe not totally organized, but a bit more organized. 因为很多的 contradiction 或者 confusion 就是从你这句话出来的。我就是要看有没有 USE 零吧，then 他们就这样吃钱咯，我把我的钱转给我老婆，我把我的钱转去那个 account， 转去别人的 account， 反正不是我的钱嘛。反正其实是我的钱，为什么？因为那个人 under 我 control。要小心啊，你要小心这个东西，很危险，很危险。你可以做坏事，但是我要知道你是在做坏事，你明白吗？这是我的 point。我要 recognize 你在做坏事，不可以超过发言。
你的解读能力，我的分析，但是你下面的解读能力可以是蛮强的，
很强哦。怎么你忽然间 agree with 我呀？忽然间心虚。所以虽然可能我不是警察，我抓不到你，我可以抓，我知道你在做坏事。OK，这开玩笑吧。But then，yeah, right，OK，讲到哪里啊？哦，诶 ，Taylor，你要讨论你的吗？还是等一下，OK，等一下，OK，好，等一下。If you still have problem with your marks, right, you should talk to me. Otherwise you keep losing mark, you don't know why later. Yeah. Because sometimes I also like misread or something like that, so you need to let me know. Okay. Right. Okay, good. I think we can proceed beyond limit laws already, I guess. Okay. So okay. Let's talk about another interesting stuff. Okay. So definition. We're gonna define something called monotone. Okay, monotone. You know what monotone is? Anyone here play music? Music? No, music here. Sorry? Yeah, 单调. Okay, 单调. Mono is one, tone is like a tune, like something like that. Okay, so why do we call it, when do we call it monotone? So one, if it is either non-decreasing or non-increasing. Okay, both cases we call it monotone. Okay, so what does it mean by these two words? Either for every n in n, an plus 1 greater than or equal to an, or respectively, we have for every n in n. Okay, so I cannot write all actually, so I should say respectively. Okay, I should say all here, and then maybe I put respectively here. Okay. So what did you see here? AN plus 1 greater equals to AN. So meaning is like kind of equal or increasing. Okay, for the case. So let me draw the picture for you. So like this. So AN plus 1 and then AN here. And then the other one is sort of decreasing, but sometimes you might get equal like some places. Okay, so we call it monotone. Can you see why monotone? Going in one direction. We're going in one direction. Okay, monotone. So in this case, actually, you can see something like a staircase also, right? You can get equal and then go up, equal, go up like that. Or equal, go down like that. Okay. So if I just put strictly less than or strictly greater, then it will be referring something called strictly monotone. Or we will throw away the word non-decreasing, it becomes increasing. Okay, increasing. So the non here is just saying that it won't go down. So it might be equal or going up. Okay, so if it's strict, then it becomes increasing. Okay, so let me write here. So if strict, then here I need to add a strictly monotone, and then this one will become increasing, and then the other one will become decreasing. Okay, so far so good. Okay, right. Oh, very sad. Am I sad? I didn't tell you it's bounded, but I told you. Oh, same. Actually, I haven't defined bounded yet. Do you have any idea what is bounded sequence mean? I think just now Chiang kind of mentioned it, right? I also draw it here already. So it's bounded above or below. Okay, so I should write it precisely. Okay, I will move this definition up later. So I should define this. A sequence AN is bounded above if there exists an M in R such that AN is less than or equals to M for all N. Okay, so we don't care this M is positive or negative, as long as it is greater or equal to all the term in the sequence. And we'll say that a sequence is bounded below if there exists an M in R such that AN is greater or equals to M for all N in. Okay, so if it is bounded, so a sequence is bounded if it is bounded above and below. Okay, or equivalently, we can say that there exists an M in R such that the absolute value of AN is less than. Does it make sense? Okay. So in this case here, AN is bounded above by M, bounded below by minus M. You might think that this definition is very symmetric, right? M and minus M. Okay. So let's say maybe I give you some examples. Let's say my sequence is bounded above by, let's say 2, bounded below by maybe -1. Okay. What M I can pick here? You can pick 5. Any other choice? Any other choice? Can you pick 1 or not? Cannot, right? Okay. But you can certainly pick 2, right? Okay. Yeah, you can pick 5 as well. Okay. You can pick 100 though. You cannot pick? What number you cannot pick? Other than 1. -1. Will be what? Say again. Will be absent. Yeah. Empty set. Huh? Yes. That's right. Yes. So you will get something like n less than a and less than minus. Okay.
Okay, good. So in this case here, actually, your M is already restricted by your absolute value because this absolute value is always greater or equal to 0. Okay, so that's mean here, if I consider this case here, this is automatically greater or equal to 0, actually, because this is secretly greater or equal to 0. Okay, good. Okay, so here we go, a very important theorem here. So monotone convergence theorem. Have you heard about it before? Calculus 1 got use this. Calculus 2, okay, calculus 2. So every bounded monotone sequence converges. Sequence converges. Okay. Or sometimes we say every bounded ultimately monotone convergence sequence converges. Okay. Yeah, ultimately. Eventually become like that. Eventually become like that. So you could imagine something like, oh, jump, but eventually something like that. Okay. Okay. Eventually, it will be non-decreasing or non-increasing. Eventually, ultimately. Before that, I don't know what it's doing. Suddenly become a good guy. Okay. Okay. But then if I just look at monotone, right, this guy will like increase to infinity, right? Could be. But then the point here is there's another condition here. It has to be bounded. Understand? So there are two things here, two things you need to consider here. So one is bounded, one is monotone. Okay, why bounded is so important? You're increasing, one day you're gonna hit the wall. You're decreasing, you one day you're gonna hit the wall. So understand? Okay, so this bound, right? This bound is like making sure that you are getting close to somewhere. But then you are either non-increasing or decreasing. So you only must get as close as possible to something. Because if it is not non-increasing, decreasing, you can do something like this. You can go up, down, up, down, up, down. Still remember there's one sequence that up, down, up, down, up, down, never converge. Still remember which one? Yes, alternating sign of -1. Up, down, up, down, up, down, you never converge. Okay, but then monotone says what? You only can go in one direction. And then you have a bound. So you will definitely hit something. Might not be this wall, like Chiang say, I can bound by something even larger. So maybe you can find the smallest bound, maybe then you can reach there. Okay, so this is the idea. So how to prove it? Okay, so this proof is very simple. Okay. Based on what we have built up. So suppose that AN is a sequence. So we prove in one direction first, not direction, one case. So which is non-decreasing. Non-increasing will be proved similarly, left as an exercise. So suppose that a sequence is non-decreasing. And in this case, bounded above is important for this case. Okay, bounded below is still okay. I doesn't care what is bounded below, but bounded above is important. So let's see. We're going to use this bound to prove convergence. Okay. Well, so let A be the set of the sequence term. Okay. I don't care it as a sequence. I just collect it as a set. So this set is actually non-empty, right? I got a sequence. So that is non-empty. Then it is bounded above. Non-empty set bounded above as a subset of real number. What do you get? Non-empty bounded above subset of real numbers. What do you get? These three things, huh? Yes, got supremum. So the least upper bound exists. Okay, so you have a least upper bound. But then what does this mean? What's the definition of upper bound? So for every epsilon greater than 0, there exists a element A epsilon in A such that this is the third definition. A epsilon greater than A minus epsilon. Okay, so how do you appreciate this thing? So your A is the upper bound, right?
your A epsilon is like this. So if you take A minus epsilon, you will go into the set.
Yeah, so a bit smaller than it is not the upper bound already. This is how you appreciate it. I think I saw a lot of you using that in your assignment. Very good. Okay. Well, so still remember what we should do here? Still remember or not? What should we do here? We want to show convergence, right? I want to show convergence. I want to show convergence. So what do you think? Any candidate you can pick here. So we want to show AN converge to something. Any candidate here? Maybe we guess it's a small a. We guess it's a small a. We guess. Okay, we guess it's a small a. So let's see if we can prove this or not. Okay, let's see if we can prove this or not. So still remember what do we need to do for this? So that is for every epsilon greater than 0, there exists an n in epsilon, sorry, n depend on epsilon such that for small n greater or equals to n epsilon, this implies that absolute value of a n minus a is less than. Okay, good. So what do you have here? You have this for free and this inequality for free. Is this inequality useful or not? If you move this inequality around, what do you get? This implies that epsilon is greater than a minus a epsilon. Okay. 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 Is it almost there? Is it almost there? Almost there. One is an, one is a. Then this a epsilon depend on epsilon. But this an here also depend on epsilon, right? So then I think you need to do something with this n epsilon. You need to pick some clever n epsilon here. Okay, which n epsilon you're gonna pick here? Okay, so how to start? Even how to start? How to prove a statement for all? Fix. Okay, fix one epsilon first. Fix one epsilon greater than 0. Now you want to find this n epsilon. Okay, so my claim is pick n epsilon such that a of n epsilon equals to a epsilon. Do you know what it means? Yeah. Such that a epsilon greater than a minus. Okay, so meaning pick this epsilon, go back to your soup definitions, find this a epsilon. This a epsilon must be something from your a, right? But something from your a should be able to express in terms of an. So pick that n to be your n epsilon. Then I claim that this will work. Okay, does it make sense? Okay, this a epsilon should come from some an. And then I call that n to be n epsilon. Let's say this a epsilon is a 100 then your n is 100. Okay, does that make sense? Okay, so let's see why it works. So we need to do calculation now. Okay. Well, so how should we continue? Let's see. Okay, so by what? By non-decreasing condition.
we actually had the absolute value of an minus a to be equals to a minus an. Is that right? Do I need to prove it to you? No. In this class, we cannot accept common sense. We have to prove everything. Okay, then in this case, this is not about non-decreasing. This is about supremum. Okay, so I think the first, okay, then maybe I don't write non-decreasing yet. Not yet there. So maybe not this, by the suit property. Okay. And suit property. And then the next part is I want to relate this thing back to n epsilon. Okay. So how to relate? So let's write down the non-decreasing condition. So non-decreasing condition says what? Condition. Because you have n greater or equals to n epsilon, right? This implies that a n should be greater or equals to a n epsilon. But then now you have minus, right? So it implies that a minus a n is less than or equals to minus a n epsilon. You swap the sign. So in this case here, I can bound it below by, bounded above by a minus a n epsilon. But then we choose a n epsilon to be a epsilon. But then we know that what's this a epsilon can give us? Can give us that a minus epsilon, a epsilon to be less than epsilon. Then it turns out that it works. Okay, so by definition, by construction, by the choice of a epsilon. This is by the choice of n epsilon. Okay, good. A question? Any question? Okay, maybe you might think that, 老师，我没有像你这样聪明耶，我可以选到这个一下子就选对耶，没有错 ，exactly. You go and try and error, try until you can build your intuition. So why you can choose that? Okay. So from here, right, there's some limited choice you can make. Okay. So for example, I write down the assumption. The assumption gives me this extra stuff. Or is this useful or not? Go and test it. Like what I do just now, right? Go and test it, and then doesn't work, and then work again, doesn't work again, like that. Okay, you can just do that. You cannot say I cannot work, I fail already. Then you really fail. Okay, so you should continue to work differently. Like just now, right? You see, multiplication doesn't work. Maybe just add a little bit more is working already. Just add these two terms. Okay, no need to do too fancy stuff. Sometimes need fancy stuff, but sometimes no. Okay, so that's why I try to control you. Don't always do fancy stuff because you will jump into the wall one day. Seriously, yeah. Okay, it's okay. You try and do, but then don't obsess with it. Okay. Question? No question. Okay, so very simple principle. I already teach up to week 4, right? Just write down your goal, write down your assumption, write down your goal, write down your assumption. Okay, it will work out. Okay, what time is it? 10:40. Are you guys happy with this proof? Theorem proving? Are you guys happy? Are you guys happy? You guys happy? Happy? The back there happy? Don't know, not happy. If don't know, meaning not happy. Yeah. Do you have question? Do you have question? No question, but you're not happy. Okay. So what do you think? You want to let me know what you're thinking? Because I don't know what you think. No, you don't know. 很难伺候我讲。
Right. If you, can you follow or not? What's your name again? Yeah, what's your name? Jingwei, yeah, Jingwei, can you follow? Okay, okay. Try to ask some question so that I know what are you confused. Otherwise, I don't know how to explain to you. Yeah. Yeah, let me know your concern so that when I explain, I can add in those concerns. Sometimes I can add examples, sometimes or drawing, something like that. Okay, but if you don't let me know, then I don't know how to. Okay. Okay, good. So let me see. So do you want to see examples on how we use this theorem? Let's see examples how to use this theorem. Yes, okay. So let's try this example then. What do you think about this sequence? Xn over n factorial. Does this converge? Okay, good, very good. So x is any positive number. An is a function, that's right. But if I fix an x, then it will just be some number to x. Yeah. If I fix an x, so for every x, it is a sequence. So if you can think of this as a function of sequence, is it what I call this? A sequence of function.
Yeah,
A sequence of function. Not right, not right. So if I fix one x, it will be a sequence. And then, so this function will output a sequence. This is what I mean. This function will output a sequence. What? Yeah, this sequence will output this function. Okay, so if you view this as a function of x, then it will output a sequence. Okay. Yes, yes. Yeah.
Oh, yeah.
Yeah. Yes, yes. Okay. Yes. So I have to talk about even general. So last time we talked about this as a sequence as a function, right? Then this is a function of two variables, if you like. Yeah.
And it's a subscript, right? So 6 and n first, and then sub like x, then you just take of that.
No. I fix x first and then for all n.
Oh, it still looks like a sequence of function because
No.
an is
So if I put a is 0.5, then it will be 0.5 to the 1 factorial, and then 0.5 squared over 2 factorial, like that.
if they want to know using the subscript a, then you have the n going, you first of all using that n.
Which n?
A subscript n.
A subscript n is to Mendel's sequence. Sequence. What do you mean? What do you mean? If you like, No. It's fine. No. I mean, like, for example, previous year you will write something like this, right? An is defined 1 over n, like that, for all n. Like that. This is how we define. This is our notation.
Yeah. So
yeah. Then here is also a sequence.
So over here your n becomes like some.
No. It's the same thing. It's just that I put here this 1 and the x is the same thing, you know. Take x equals to 1 is the same. It's the same thing I wrote just now. Okay. Yeah. So you should think of this x as a fixed x first. Okay, because I fixed x, and then look at this for all as a sequence. Okay. You can wait. You go back and wait first. Later I can go discuss with you. But then there's nothing to debate here. Right?
You can debate later. You can debate later. Yeah. But then, is anyone okay with this notation? Anyone okay? Maybe I ask Yung Sun. Sorry. Hongjing. Yeah. Hongjing, can you get this notation? Can you get this notation?
I already write down example.
Okay. So do you think what this converge to? What do you think? Does this converge or not? Maybe you try some number lah. You try some number. Okay.
If you just look at this, what do you think? How about this number here? What do you think about this number? Is it getting close to any number? Who say? 0, right? Okay, 0. But then you want to test another number, let's say 1000. Is this sequence still getting to 0? 1000. Maybe the first few terms looks still a little big lah. But then if you try and use computer to see, you can see that actually the n factorial increase faster than the much faster. It's not just faster. We have to be a lot faster so that it can converge to 0. Okay, so actually we try to argue that this thing actually converges to 0. Okay, so maybe I write here fix x 0, and then this sequence here will converge to 0. Okay, so how do we prove? How do we prove this? It's the same thing lah. In mathematics, we write for all x and then fix x is the same thing, you know. It's the same. It's the same. If you just say fix this is true for all x, so you need to be how to say sequence. You need to get used to this thing. For all and fix is the same. Yeah, okay. But then it's the same thing. It's the same thing. Right. If it's not the same, it's just that I'm looking at all the I look at as a function, like what you said, for all x. I look at a function, so it's a sequence of sequence. I mean, I cannot say sequence of sequence. It's a bunch of sequence. Yeah. If I write like this, okay, it's not the same thing. True, I accept. But this is that I have a bunch of sequence. Yeah, that's it. So I'm looking at different an like that. Yeah, you are true. That's why I removed this so that I said that this sequence converges to 0. Every one of them. Yeah. It's better for me to write conversion. But then if I just write for all, I'm looking at all of these. If I fix one, I just look at one sequence. Understand? If I fix one, I look at one. If for all, then I look at all possible. But I wanted to say all of them will go to 0 also. In the end, I'm saying the same thing. You understand? Okay, can understand what I say? So I mean, like all these sequence will converge to 0. Yeah. Okay. So how do we do this? How do we do this? Okay. So array. Oh, very good. Ratio test. Okay. Ratio test. Okay, very good ratio test. I think if possible, towards the end of this class, we will introduce ratio test and then we will introduce the proof. And then at that time, I think you can appreciate the proof already after we learn all this. But then now we don't have ratio test at our disposal. But then we will have this monotone convergence theorem. Okay, so then we need to show two things. One is monotone, one is bounded. Okay, one is bounded. Okay, so so can you roughly guess what's the picture of this sequence? Roughly guess. Just now you say this is 0, right? Can you see what's this picture giving you? Decreasing, decreasing, or another word, non-decrease or non-increasing is enough. Okay, so let's see we have non-increasing or not. Okay, so let's check. So let's check. Times is up. N plus 1 minus an. Okay, so do we quickly do it? Let's quickly do it.
Okay, if we put it up, what do I get here? X minus n plus 1. Okay, can we make this less than 0? Is it possible? N is large. Yes.
Plus one.
Yeah. So the key is this part, right? Okay, if you can make this part less than 0, it's good already. Because I don't think you can make this part less than 0. Because x is positive or n is positive. You cannot make that less than 0. But if you can make this less than 0, it's enough. So what does this mean? This means here your n has to be greater than x minus 1.
Okay, so you just pick this large of n. You can see that this is a ultimately non-increasing sequence. Okay, this large. Before that, not shown.
Okay. So that is. So this n is really depending on your x. So makes sense, right? Depend on your x. Okay, so that is an is non-increasing for n large. Okay, so if it's non-increasing, your monotone theorem need bounded below or bounded above. The decreasing, right? Yeah. So you should aim for the greatest lower bound. Yeah. Okay, the infimum. Okay, so also an greater than or equal to 0 for every n, so that the sequence is bounded above because it's everything positive there, right? Bounded below, sorry. Okay. So so this sequence converges. But then how to find the limit? By monotone convergence theorem. Okay, how to find the limit? Maybe you can use the epsilon delta thing to help you lah. But then I'm not sure it's hard or not. Meaning you need to show this thing. So if you check from definition, directly prove from definition, what you need to show is you need to show the absolute value of xn over n factorial is less than epsilon. I'm not sure you can pick this n epsilon nice or not. I'm not sure. Maybe you can try. You can try. What's formula? Stirling formula. Approximation. Yeah, I know. So I'm not sure. You can try write it up. I'm not sure, but then you can observe one thing is observe that the relation between an plus 1 and an. What's the difference between them? You got an extra x and the extra n plus 1. Okay.
But then we know that this term converge, and what else we know? This is a constant, right? And then 1 over n plus 1 also converge, right? We know. Okay, so on the right hand side here is 3 convergent sequence multiplied together.
So we can use limit law. Okay, so a equals to limit of an plus 1 equals to x times limit of n to infinity of 1 over n plus 1 and limit of n to infinity of an. Okay, but then we know that limit of an is just some limit that we know, but then the middle part there's a 0 here, so we get 0. Okay.
This one we know. Do we know this? I think we proved this for 1 over n, but then 1 over n plus 1 should be 0.
Why?
Yes.
You seem to assume that it converges, and then use the A itself to show that.
Yeah, I proved that this converges, right? I just now proved to you that an converges. And then 1 over n plus 1 also converges, because I think last time we showed for 1 over n. Then x is just a constant, so it definitely converges. So it's a product of 3 convergence, so we can use limit.
Okay, so this part we use limit law. And then this part is the monotone convergence theorem. And then this part as well, monotone convergence theorem. So from this calculation, it seems that your limit is controlled by this 1 over n. Yep. Okay. Right. Any question? No? Okay. No ratio test, huh? No ratio test yet. Okay. I think towards the end we will have that. But then now no ratio test. Okay, so see you tomorrow. Okay, see you tomorrow. So tomorrow there's a quiz. So is there a convergence? I haven't decided yet actually, so I can tell you. Yeah, I'm still thinking about it. But there will be something on absolute value. I can tell you a bit. Yeah, absolute value. Yeah. Okay, so see you tomorrow. 怎么样？来看一下这个 focus 不要讲的是啊，等一下。